Okay, cool. Hi, everyone. My name is Xudong Fan, and I'm a fourth-year PhD student from Case Western Reserve University, and my supervisor is Dr. Yu. So as you can see here, my topic today is about the artificial intelligence aided decision making in critical infrastructure networks. So this picture shows a very concept trajectory curve of a system performance in its lifespan. So basically, we are looking at the system performance. So also basically, the x-axis is the time span of infrastructure system, and the y-axis is the system performance. So basically, we are looking at three phases in the life cycle. First is we named it the pre-disaster phase, which is also our routine, which is where the routine maintenance involved. And when there is a hazard happens, we will look at we will see a significant drop of the system performance. So after this point, we are looking at the recovery phase, which means we need to do some decision making in this stage to obtain optimal recovery trajectory rather than this less optimal recovery. So if we are looking at these two trajectories, we can see if we can adopt a more optimal recovery, it can achieve a certain threshold of system performance more efficiently, and also it can achieve a higher error under the curve, which we often say, which if we are using this area of under curve as a resilience index, we can say optimal recovery can achieve a higher resilience index as well. So in this presentation, I'm going to talk a little the research about how we are going to use the artificial intelligence to add optimal restoration decision making. So we are going to make this problem as simple but fundamental as when we are looking at a network like the left graph, and we have many road segments failure at the same time. How are we going to recover this road network to make the system more resilient? So although this assumption is quite simple, but we think this assumption can be easily extended to multiple applications. So with that said, we are going to take this recovery process as an optimization problem. We do have some approaches already existed, including the global optimization approach, which we are going to try to achieve the highest error under the curve, as you see from the last image. So some famous global optimization algorithm include the genetic algorithm and the mixed integer optimization algorithm. And if we would like to, and also we can take the problem as a localization optimization approach, which means in every time step we always repair the road segment that can improve the system performance the largest. However, the localization optimization will trap into localization optimized rather than a global optimized. So that is the thing that we would like to avoid. The last and the less computational complexity method is a so-called surrogate importance index. Some quite often used index include the betweenness centrality index, which is a method to measure the betweenness centrality degree of each road segment. And also we can repair the road segment based on its distance to some emergency resources. We can repair the roads that close to the emergency response team, and then repair the other one. And the last surrogate index is the road hierarchy. So however, we do have some limitations of this method. For example, for the global optimization approach and the localization optimization approach, it is easier for us to customize our optimization object, which means we can always consider other factors such as traffic load, the connectivity, or and even nearby communities into our optimization object. However, these types of optimization algorithm is really hard to consider the network topology. For the surrogate importance index, we do see that most of these methods are based on the network topology. However, it's really difficult to consider multiple factors into our optimization process. For example, when we are looking at this betweenness neutrality index, it's easier. It only considers the network connectivity, so it will always try to improve the network connectivity. But if we would like to consider other factors such as the reliability degree of each road segment, or if we would like to consider the community that each road segment serves, it's important to consider these factors. So similar to the other methods. So in my research, we considered a critical question is, can we consider both? Can we try to customize our optimization object as well as consider the network topology in the decision process? So we would like to leverage two algorithms here. The first is the graph convolutional neural networks and the deep reinforcement learning process in our decision process. So with that said, we are here to define the road network recovery as a Markup process. So which means at each time step, we are going to get an update state of our road network. And based on the current state, we would like to find an action, which means we would like to find which road segment we should repair to achieve the global optimization. And based on the action, based on the road segment of repair, we can always get a reward of our action, which means how much the system performance is improved. So I'm going to explain this Markup process one step by one step. First, we do have the state of the network. Remember that we really would like to consider the network topology in our optimization process. So we are going to use this adjancent matrix to describe our road network. If you can, of course, this adjancent matrix does not represent to the road network I showed here. It's just a concept adjancent matrix. So this adjancent matrix is often used to describe the road network for the integers of 0 or 1 in between the nodes. Also, this A, B, C, D, E represents the junctions in the network. And if two junctions are connected, we are going to use an integer 1 to represent the link. If these two junctions are not connected, we are going to use the 0. And but in our proposed adjancent matrix, we are trying to use the so-called average number of reliable independent pathways to represent the values of each node. So which means we are going to replace this zeros by the average number of reliable independent pathways. So it should be mentioned that this value of the reliable independent pathways is proposed by Dr. Wang in 2016. We do not modify any factor in their equations for the system performance evaluation. So basically, we directly applied a resilience concept that's already proposed in the previous study. So with that said, we already have found a way to represent the current state of the network, road network. In here, we are going to evaluate the current system performance of this road network. So this basically the system performance evaluated by the summary of the average number of reliable independent pathways of each junction and multiplied by its weight. This weight is actually represents the junction's distance to its nearest emergency response station. So again, this system performance is directly adopted from this literature, and we just would like to test our optimization algorithms. So, and again, in the recovery decision process at each time step, we have an action to make. So in this study, we are trying to do the decision as simple as like which segment should we going to repair. So this is our action here. So of course, after no matter which road segment we repaired, the system performance will improve. So we are going to use the difference between the before and after taking this action as a reward of this action. With this side, I'm going to introduce the proposed training and decision framework to make the optimal decision making. So as the first, we are going to, of course, initialize the traffic network damage situation, because we always need to start with a kind of damage, right? So after we get the damage situation, we are going to feed this network into our JSON DRL model, and this model will give us a recovery sequential, like how should we recover this road network. So we are going to record the repairing sequence, and we are going to record the current training times. So after the training times exceeds the predefined number, we are going to say, okay, we are pretty satisfied with the training process, and we are going to end here. So as you can see in this process, the most important thing is that how we are going to train our JSON DRL model to make it to predict the most optimal recovery sequential. So in here we introduce the JSON DRL model as shown in this picture. So basically, at the beginning, we are going to input the current state of road network, and we are going to put this road network into 2 layers of graph convolutional neural network, and we average the output of the graph convolutional neural network by using 2 layers of normal neural network blocks. So the last layer of the neural network will give us the action that we should take under the given current state. As you may say, like at the beginning, all the neural networks weights and the bears are randomly initialized, which means this action is also randomly derived. However, if after we get this action, we are able to know the next stage of this road network. And here we are going to split the passes into two passes. If you are looking at this dashed line, we can compare the states before and after taking this action, and we can get the instant reward of taking this action. On the other hand, on the other path, we can feed this state into the graph convolutional neural network again and get the highest future rewards with this given state. So after combining these two rewards at here, we are going to use a very famous equation called Bowman Equation to get to estimate the true reward of this action. So although you may think that this process is totally random, but remember that when we're repeating this process, we always involve a true value, which is the instant reward. So for any actions, we always know this instant reward of each action. So which means after training this model 1,000 or even tens of thousands times, this graph convolutional neural network can predict the real value for global optimization of each action more and more efficient. So if we go back to this process after we finish the training process, we can always save the graph convolutional neural network model parameters in our local disk. So so with that trained model, the decision-making process is quite straightforward. We are going to put the traffic damage situation into the trained graph convolutional neural network model, and this model will choose the optimal repair road segment, and we repair that road segment, and we update the traffic network, and then we repeat this process. So with this proposed graph convolutional neural network training and decision-making framework, I would like to use two case studies to validate the proposed framework. First, the case study is that we are going to make the decisions with knowing initial damage situation, which means we know the initial damage situation looks like. So in here, we are going to use a real-world road network from California. And we also have a separate program that uses to do the seismic simulation. So actually, the right picture here is actually the result of the seismic simulation. We do have the road segment reliability after seismic. For example, the 0 means this, or the 1 means 100% reliability means this road segment is intact, and there are some other road segments that suffer different types of damage. And we do, and a quick statistic summary of this network is we do have over 100 road segments and 19 street junctions. And also we have a few assumptions here is at each time step we only repair one road segment. The road reliability will recover to 1 after the repairment, and the repair time of each road segment is assumed as 1 day. The network performance re-evaluated after each repair, and the restoration finished when all the road reliability is recovered to 1. So we let our graph convolutional neural network, or we call it artificial intelligence agent, try 1,500 different repair sequences, and we can observe its learning trajectory. Basically, we can see here the x-axis means the training time of our AI agent, and each train time represents a full recovery trail. The y-axis means the resilience of index of that recovery trail. So the resilience index is the sum of the system performance at each time step. So basically, we are conducting more than 200,000 times of decision making of this AI agent, because for each full recovery we have to make 136 decisions, and so to compare the performance of the proposed graphing AI agent, we take another two methods as a benchmark. The first is a genetic algorithm, which is also a global optimization algorithm, and we also let the genetic algorithm tried 1,500 times. So they try the same time. And if the result of the genetic algorithm is showing here as a shared area, we select the most optimal recovery trajectory as the upper line, and the lower trajectory means the worst scenario, or the worst recovery decisions. And we also consider the betweenness centrality. Remember that the betweenness centrality can only consider the connectivity of the network, and without the road segment reliability, we can say that betweenness centrality performs good, but still worse than our proposed AI agent graph convolutional neural network model. So, however, we still face a critical problem is that training such a model is quite time consuming. It is really not good for the emergency response after a hazard. So we would like to, so my research also considers that is there any possible that we can pre-train artificial intelligence agent pre the disaster, and this agent can be used for any new disasters without retraining. So with that motivation, we consider this case study too. The road network we select is from the University Heights in Cleveland, Ohio, and we have over 140 road segments we have 95 junctions here. But we consider another hazard here, which is a flooding hazard. We do have another flooding simulation program besides this project. So we use that program so that program can help us randomly generate the flooding hazard scenario. However, another assumption is that we consider the reliability of each road is either 0 or 1. So basically, in this study, we only consider the connectivity of this network rather than others. With this assumption, we can think that the between centrality prioritized method can be seen as a near optimal solution. So this method will be used as a benchmark of this case study. Again, if we go back to our decision-making process, in order to train an AI agent that can take care of any possible damage situations, we will randomly initialize this. We are going to randomly reinitialize this damage situation during the training process. So again, the well-trained AI after, if we keep continually change this damage situation here, the AI agent model can be trained and stored in our local disk. So, and then with this trained model, we are going to use this model for the decision making for the new damage scenario. So because due to the extreme large state action combination space, we increase the training times to 4,000 times. So again, each training episode or each training process means means a whole recovery process, and we randomly reinitialize the damage situation, and we can see this training results show a much more significant fluctuation compared to the previous study, because previous study we always start with the same damage scenario. However, we would like to test our trained AI agent with new damage situations. Here we propose the 4 very randomly damage situations. These damage scenarios have never been seen for our AI agent in the training process. And we compared 3 methods. First is a specific graph convolutional neural network model. So this model is trained for each damage situation purposely. So what we did here is exactly the same with case study 1. And the second method is the pre-trained graph convolutional neural network model, which we just did. And we are going to use the pre-trained model to solve these 4 damage situations. And again, the between centrality prioritized method is going to use the benchmark as it provides a near optimal solution. So in here, we can see the resilience index that achieved by these 3 methods are showing here for each scenario. We do see that all of these 3 methods achieved quite similar resilience index, which means all of these methods can achieve acceptable recovery decisions. However, if we are going to look at the computing time of this method, we can see the specific graph convolutional neural network model always takes more than like 2 hours to finish the training. However, for the pre-trained model and the between centrality model, we only need a few seconds. So this is a huge benefit of this framework, because it can be trained before the hazard happens and use the model for the decision making after damage situation happens. So with that said, here is the conclusion of our current study. Is the graph convolutional neural network provides a novel way to let the machine understand the network structure, and the deep reinforcement learning provides a appropriate learning framework to let the machine make optimal decisions. For the case study 1, it demonstrates the proposed framework achieves better performance than genetic algorithm, because the genetic algorithm cannot consider the graph topology. For the case study 2, it demonstrates that the the proposed framework has the ability to be trained before the hazard happens and make efficient decisions. For the surrogate method, such as the between centrality method, it can only be efficient when only the network connectivity is considered. However, we can say in the future, the definition of resilience will consider more and more factors, which requires us to have a better solution to make the more optimal decision. So, yeah, thanks for your attention. I would like to take care of any questions.